So welcome everyone to this edition of the Virtual Time Series seminar. It's my great pleasure today to introduce our speaker, Hashem Pesaran, who is accompanied by our guest panelist, Jörg Breitung. And the title of the talk is Analysis of Multiple Long-Run Relations in Panel Data Models. Hashem, the floor is yours. Thank you very much for joining us.
Thanks so much, Majid, and thanks so much for Jörg to agree to discuss this paper. As you see from the slide, hopefully, that this is a joint work with Alec Chudik and Ron Smith, some of my co-authors in many other papers or related papers. You may say, why write another paper or think about this problem about long-run relationships? There is obviously huge literature out there. And the way to think about the problem here is that first we're dealing with panel, not single country or single unit to do the long-run analysis. Obviously, if you have a single time series, a vector of time series, that's a different problem. The second is that although there are panel version of like co-integration, and a number of them I have, and our discussion has contributed significantly to that literature. The problem with that that literature is that it's the number of data points time series T, cap T, must be much larger than the number of units that are included in the panel. And allowing for panel is also help us to deal with latent factors, which we cannot deal with if you deal with a single time series. So using a panel become important, like we're dealing with data or across firms, because the number of firms are much larger, the sample period over which the firms are observed. Or if you look at even countries, you don't have large amount of data in terms of time, but there may be many countries. There's, for example, climate literature, which is moving on. They have 170 countries, but the time period, because output data is short, is maybe 50 or 60 unbalanced panel. So the literature here is really focusing when n is larger than t. How do I mean n larger than t? Before I go into it, I used to use at the relative rate like a root n divided by t. I think that's not a good idea. It's not precise enough. So the way we look at it is we say, imagine t rises with n at the rate of n to power d. That d I'm going to use. So if d is 0, t is fixed. If d is 1, n and t grow at the same rate. What about if d is less than 1? That will be dealing about half, say. So in that case, t rises much slower than n. So if the way to think about it, as we're going to explain, the difference between the work I'm presenting here and the sort of the literature on co-integration is exactly to do with d. They have to assume d larger than 1. I'm going to assume d is larger than a half. So that's the difference. And also like to see whether anybody can come up with a method using the old literature to beat this methodology we have developed. So it's a challenge, okay? So what is the problem? It's a well-known problem. Suppose you have vector of m dimensional. M is not large, although you could go back and say, what we did with large var, people have looked at it, but then they stack all the w. So I get n large with the w if it's stacked. In other words, you have a vector of wt, which include w1, w2, and so on, because then the dimension of the vector of wt would be m by n, since n go to infinity, so therefore is also a large var, effectively, if you see what I mean. But we are splitting it because we understand units, like we know what is the w1, w2. So therefore, that's what the wm is fixed. So it's not a restriction in my view. So then, and the number of units is large and larger than t. Although we are not saying we have a method for t fixed and going to infinity. Although the results, Monte Carlo results, suggest t doesn't have to be very large. even when n is 3,000. And that's the achievement of this method, in my view. But I leave it as I do. I do a lot of this thing, and I wait for others to decide, because no point me advertising something because I'm biased, because I'm the developer of the idea, and with my co-author usually don't believe me to begin with, but then when they do the Monte Carlo, they all agree with me. But that's what it is. So I'm hoping that you guys try it at least after this meeting. There are lots of data set which has to be analyzed, which previously wasn't available to the, wasn't applicable to the old techniques. So we look at panel, it's like Penword table, or you could look at data from compute stats, so firm data, country data, region data, county data, all of these where T is not that large and very large. Like there are 3,000 counties in the US. I'm sure most people could probably get hold of that data and analyze it for many, I use that data for predicting the presidential election. That's a different topic. So basically, I don't want to go into the literature. There's a large literature. We can come back to it, but I think it's better just move on to what we do and then talk about how does it differentiation. I'm sure maybe that's what the discussion would also address. So what is the basic idea? The basic idea is you're starting with the general linear model. So I don't start with the var. If you remember Johansson approach, they have to move into a var in order to apply the Johansson technique. And often then, if there's a moving average component, I think this is what Majid also knows, then var will not be really accurate representation. So the first thing we do, we don't really start with the var. We start with the general linear model. So this is the model for each country, or each unit. Effectively, we do a fixed effect. This is a panel. So AI has to be free. We don't want to restrict it or assume it's the same or uncorrelated with V. It could be correlated with V. So it's very general. Then the VI is effectively a stationary component, which is defined in terms of the primitive errors, which are UI. So UI are obviously going to be serially independent over time, but V is a stationary. So that's a station component. That's well known. This is called also Granger representation, if you like, but that's well known. And then the key is that the SI is the unit root process. And obviously, if CI is zero, is everything is stationary. There is no point talking about long run relation. So here we assume that obviously CI is not zero, and therefore that give rise to a unit root in the W for each I. Of course, you can look at this for each I. By the way, we can apply this for each country and then average, what I call mean group estimation. But we're not doing it today because I'm interested in pooling method. Okay. Somebody commented, can you do it? I say, yes, but not in this paper. So therefore, it can be done. Most of you know what I've done. I think I can do it. It's not a problem. So I can do each country separately and then average. So I love heterogeneity much more generally. It's not a problem. So basically, then what are the key assumptions? We need to assume that this station component is really stationary. In other words, these matrices, the sort of the norm of these matrices, all of them, without exception, all of them are bounded by rho to power L, where rho is less than 1 strictly. So because if you allow rho gets near 1 now, in addition the S, you get fractal processes, you get long memory processes, which we need to avoid. Okay. All right, so that's the model. Now, of course, you may say, what about common factor? We do allow for it. I'll come back to that. So let's just understand the problem without latent factors. Then we come and see what happens if you have latent factors. In fact, my co-authors often like to write it more generally. I always push them towards a more simpler problem when we present. Okay, so that's the basic model. Okay, so what is the issue? The issue is that the CI is rank deficient. That's the long run relation. And the rank of CI tell you about how many long run relations they are, because the number of variables is m. If the rank is m minus r naught, then R naught would be the number of long-run relations. So what we want to do in this paper, we are wanting to know what R naught is, one parameter of interest, and also find out what are the co-integrating relations, which is there would be R of them, which all of them, when they multiply by CI, go to 0. Again, this is all in original co-integrating literature. There's nothing unusual on here. But what is unusual here, notice here, although there is an I here, rank of CI, there is no I on R naught or I or M. We want to pool. Otherwise, if I say everything is totally different, it doesn't, to me, you don't get the benefit of pooling if there is a logic in pooling. Why I think the pooling is relevant here? When I worked on co-integration, one of the attraction of it to me was that, like PPP, person power parity, is a long-run relation. You would expect it to be common across all countries. You can't, if you have equilibrium in the world economy, you can't have them different. For example, if you're dealing with the relation between investment and output, and the co-integration coefficient is 1 and -1, you would expect it to be the same across all countries. So basically, this is where it. If they are not the same, as I said, you have to do country by country and then average. We call it mean group estimation. We are not doing it in this paper, but it can be done. Okay, so what we're interested is R naught, which is common across all countries, and what we are interested in the B naught matrix, basically, which is the rank of it is clearly it matches with the order of this. So, for example, each beta j naught would be m by 1, and there are R naught of them. So B naught would be obviously m by R naught. So that's what we want. So of course there's identification. It's very obvious. We know that because I can put a matrix between beta and W, which is of order R, and then rotate the beta. So obviously we need to have some restriction to identify the beta. But for estimation of R naught, you don't need any identification of beta naturally. Okay. So what about if there is a factor in there? Okay, suppose I put a latent factor. So that's really general model. I mean, when I was looking at it, I thought it may not work, but it's just actually quite interesting how it would work. Although I'm not going to go in detail in this paper. It would be in the revised version. So think of a model like this now. Suppose you put the GI, which obviously would be M by the number of factors, MF now. MF doesn't have to be the same as the number of M, obviously. It could be 1. So there's only one latent factors. Now, if that's the case, the only way that you get co-integration, if you have to have cofactoring, right? This is not in the paper box. I'm sorry. This is an addition to what we're working on. So basically, it's like co-trending. I mean, if you look at the book I wrote, I realized that co-integration is not enough if the trends are different, right? I mean, the diverge. So co-trending is more important than co-integration. Okay. So basically, there are two possibilities. Either F is I naught. No, it's like another error. You push it to the V, right? So the paper, the model works. This is in the paper. But even F is I1, it would work so long as you also assume the restriction beta, the same beta naught should also, which get rid of the CI. In other words, when you have beta naught prime CI becomes 0, should also have beta naught prime GI 0. If it's not, it means cannot be a long-run relation. So you need both co-integrating and co-factoring in this model, okay? So it's a new idea. It's not new, it's obvious in a way. I mean, you can't have co-integration without co-factoring if the factors are unit root. Since we don't know whether the factors are unit root, we need a method which works either way. And the method we have actually works either way. We can show you some Monte Carlo. And as soon as people, my co-authors mentioned this, that people worry about it when they present the paper once Alex did, I said, well, it's not a problem. I don't see that's an issue. Okay, so we'll see why. So this is just, I'm going to back to the baseline model, which is normal F, but I mean, I wait for people to tell me I'm wrong, but I think it's right. It doesn't matter. You can put F there. If it is I naught, it doesn't matter at all. If it is I1, it should be cofactoring. That's the end of that part. Okay. Let's just go back to the simple model. So what is the basic idea? One thing I learned in panel, you want to get rid of what we call nuisance parameters. Here, AI is nuisance, but CI is not nuisance. So the way to get rid of AI, the usual what people do in a panel, which I have done, when T is short, you first difference, or you demean. If you demean, it won't work. Everybody knows that. It's called like the nickel bios or whatever, but here is much more complicated. So innovation of this paper is to get rid of AI by subsampling. So this new. I mean, I'll wait and see whether somebody else has done it, but let's just see. Okay, how it works, I think the best way to think about, you subsample Q, you have non-overlapping samples. So let's imagine the time is order. The best way to understand this problem, imagine Q is 2. In fact, it turns out most of our Monte Carlo result, for a reason I'm going to explain later, Q2 is enough. So you don't need more than 2 subsamples. Okay. Let's just say 2, Q is 2. So what you do, suppose you have 100 years of data. You split it into 250 years, the first 50 and the second 50, no overlap. Don't worry, some people say, well, when you do 50, why don't we drop something between the two? It doesn't matter because it's irrelevant. T going to infinity at some rate. So it is not, mathematically, is not important. So basically, what you do, you average this over the 2 subsamples. Say L is effectively the number of subsamples going from L from 1 to Q. So when you do that, you subtract the 2 from each other, from the total. So you do subsample 1, and you subtract it from the whole of the average. These are time averages, okay? It is opposite to the way you get rid of AI. You just don't look at, you basically take 2 subsamples, you subtract the average from each subsample from the total, and obviously AI drops out. So you end up with the equation in the bottom of this slide, which hopefully people see, which basically says the average of is all for each unit, by the way. I haven't pooled yet, right? Pooling comes later. So here I'm dealing with each unit. I'm taking the subsample L, which is first, let's say L is 1 and 2. First half, this average on the first half of the unit I, minus when you put naught here, it means the full sample. 0 means full here. You subtract them. So what happened? You get CI. The I would drop off clearly. You get CI multiplied by the difference between, these are more complicated processes now, because remember, each SI is a unit root. Now you're averaging over unit root, over 2 subsamples, right? That's the complication. These ones don't matter so much because they are stationary. Any average is stationary. Okay, if it goes to infinity faster. Okay, the thing is that the rate at which these subsamples go to infinity differ. That's the key result, and that we use that to separate the signal from the noise. So therefore, these are also nuisance for identification of CI, but we can't get rid of them. The V cannot get rid of them. But I don't worry that I can't get rid of them because they become dominant by the first term. Unless CI is got rid of. And that's why we can find out the rank of the matrix and also the long run. So that's the basic idea. The rest of them is algebra and luck that your idea works. Okay, so if any question, I'm happy to answer. So can you see, this is the reason why I've written it like that, because if you take the average of something over the full sample and then you have 2 sub-averages, average of the 2 become the same as average of the total, right? So basically this become average of average of the subsamples. That's just the, like arithmetic, result. It just happens. There's no question, I can move on. Okay, so again, stay with the unit I. Now I generate, sorry, I should have gone. So what I do now this is a vector. I want to look at the basically variation of this over L, right? Because L is changing from 1, 2, 3. So I'm going now to pool across the subsamples before pooling across I. Okay. Okay. So you basically define a matrix which we call Q WI bar WI bar, and that's just simply sort of a covariance matrix, a sample covariance matrix of subs across subsamples. So we divide by T because otherwise it would blow up. So it's just a scaling. And you have to divide by T because of this SI. Because SI is an average of the random walk processes and it rises at the rate of root T. It's heuristically. We are not using this in proofs. We do proper proofing. Because of when you average over I, you can't just do each of them, right? So don't think that this is the proof, right? This is just to show you why we divide by T, right? Because if you multiply by root T and multiply by root T, you get T, then you have to divide by T to stabilize it. Okay, that's literally come. And the Q is just the number of subsamples. It's averaging over Q, you divide by Q. But Q is immaterial because it's fixed. Oh, by the way, yes, number of subsamples don't go to infinity, it's fixed. That's the basic idea. So therefore, you can see here, you can guess that this QVVI would be not going to rise, it would be stable, right? But these ones are going to be more important. The first three terms dominate this last term. And you will see without CI put to 0 or get rid of, the first term dominate the second terms. Okay. All right. Now, that is where I keep saying, if people want me to be very heterogeneous, when I become very heterogeneous, people complain it's too heterogeneous. When I write something poor, they say, why did you do heterogeneous? Okay, so I'm forced to say that today. I can easily do heterogeneous. Why? Because if T large enough, right, I can multiply this matrix Q by beta naught or beta I being the ith unit. Now, if it's co-integrated, it would annihilate the first one, annihilate the second, the third one. Therefore, I end up with this and the last one, and I can then show you that's co-integrated. You can estimate it from that. So even you have a single country, this method works. But then you need T very large. So this method can deal with heterogeneity. I'm not doing it, okay? Because I said most application, in order to really understand, you need to have commonality across units. So why do you do panel? Even when I do heterogeneous, I look at the average, most of you know. I don't look at individual units, right? If you want to look at individual units, that's a different problem. I don't think, we need large T, right? Okay, so now pooling. So now assume that there is a common R node, which I said. Well, I'm sorry, before we're going that, it's very easy to prove that this guy, the C is dominant, this part is dominant, the rest become small. So now pooling, so what we do now, you average across N. It's very like a fixed effect. A lot of people think fixed effect was efficient. It's not efficient because fixed effect just pools without weighting, right? If you look at the fixed effect, you just sum the covariances of each unit. It's the same as this. But then you don't divide by the precision of each unit, right? Because that's very difficult to know what the precision is when T is small. So that's why it's not efficient, but it's robust. So it's the same way here. So what we do, we just put equal weights across all units. People, if they know better, they can put a little WI or a little lambda I in front of these Q matrices before you pool. But I leave younger people to do these things. They like to do these things. I don't like it. I like equal weights. I learned from Bernoulli. It's called the principle of insufficient reason. When you have any reason to believe one thing is different from another, you put them equal weights. Okay. So I like equal weights. Now, then, what are the assumptions? So this is what we're going to do. This is the object of the statistical analysis. It's simple as that. It's just a pooled covariance matrix. That's why later on we call this pool, look at the eigenvalue of this. So that's what we're going to call the matrix, like an eigenvalue problem. By the way, it's related to the original work of Phillips and Doelof, which they look at one unit and they looked at the covariance, but they do look at the specular density as zero frequency. And that was their problem, in my view. They didn't do subsampling to get rid of these issues. What they did, they look at specular density as zero frequency. And everybody knows, I knew at the time, when Yongshol Shin came to Cambridge, told me about it, I say it's like between devil and blue sea. It's a devil and what's called blue sea or something, which basically in order to get the specular density right, you need to somehow increase the window, right? As you get to increase the window, T has to become larger and larger, and usually it doesn't work. They have tried it. So here is an innovative way, even if you want to do it along the like eigenvalue things, this is what we're doing. So basically, the reason why it happens, notice here, if I post-multiply this by beta naught, it becomes C prime I beta naught. That goes to 0. And then obviously we need to know what happens here. But you can just see that therefore suddenly this matrix would have to have an eigenvalue near 0 for that to happen, because it goes to 0. So therefore, it means that the beta, the eigenvector, which corresponding to the smallest eigenvalue of this Q matrix, would be the cointegrating vector, if there is one. Well, the same happened to pooling. In pooling, it increases the power of this, because if I multiply both sides of this by beta naught, suppose that's what I think is cointegrating vector, this will go to 0. And therefore, beta prime multiplied by Q becomes 0. Therefore, it has beta naught has to correspond to the lowest eigenvalue. Assumptions, very basic assumption. You don't need really anything unusual. You allow for obviously errors have to be independent, but remember we allow for the general linear process. I mean, it's just normal assumption. We don't put any restriction on the dynamics except apart from unit root, everything is stationary. And then obviously the covariance matrix of sigma I could be whatever you like. It has to be obviously positive definite, although I'm not sure whether you need positive definiteness in this paper. The key assumption is about this rate at which the CIs, the norm of let's say the memory of the process at the neural level has to be short. Having got this assumption, then you can make this the very important result for the paper, I mean. So you can show that QWW is equal to this expression, and pooling helps you because that goes to 0. This is lower order because remember, these are stationary component goes to 0 because we have to divide by T to stabilize this. And the key is the Q matrix of the random walk component. And that is the most important result of the paper. It took me ages. I mean, I started looking at it during COVID, believe it or not, is being bored with COVID. So I said, well, let me see what happens. And this is the exact result. And it's quite clear you need 2 subsamples. Q cannot be 1. It's obvious, right? If my math was wrong, we say Q doesn't, it could be 1, right? Clearly it cannot be 1. But they only need to be 2. The other thing is that when T becomes large, it's of order 1T squared. So everything becomes Q minus 1 divided by 6Q multiplied by sigma I. Now, if you then look at the average of all this, this is for each I, this becomes the average. So therefore, QWW bar becomes this, because that's this 1 over 2 squared is lower order. So we get this important result, which basically says that the object of interest is this the data. The left-hand side you can get from the data. The right-hand side is the theory of it. These are going to zero when n and t become large. So the thing is, therefore, if I post-multiply this Q matrix by beta, some vector, if it also get rid of psi n, it means that is eigenvector associated with the smallest eigenvalue of Q. Right? That's heuristically. Why? Because if you multiply beta, post-multiply or pre-multiply, doesn't really matter. If post-multiply by beta, again, that becomes zero. Because remember, we're saying C prime I beta naught is zero for all I. That's pooling condition. As I said, if you don't want to do this, you have to go and do each country separately or each unit separately. We are not doing it in this paper, but it can be done. So therefore, then it becomes clear that you can then separate start from the lowest eigenvalue from 1 to R naught would be all zero. And if you go to higher eigenvalue, would not be zero. So that creates a separation. And then obviously the theory is to prove that what the intuition, which this result suggests, is hold. So we then effectively go to multiply by beta naught now. If you multiply by beta naught, any j going from 1 to R naught, these are all go to zero at these rates. You need t go to infinity, but t go to infinity doesn't have to go to infinity as fast as n, because this goes to infinity at the rate of 1 over root n. This goes to infinity at the rate of 1 over t. That's why you don't need as big of a t as n. Okay, that's now mechanics. How do you go about estimating? So suppose you want to apply this method. What do you need to do? You do subsampling, Q of them. Of course, we have to decide what Q is. We're going to argue Q2 is enough, and in fact, better than any other measure, but there is a trade-off as usual. But let's say Q is 2. You just do 2 subsample, half the data. A lot of people ask me, what about your data point is odd? I said, drop one of the observations. Don't worry about it. It's still going to infinity. Drop the first one. So people ask me such, I don't know, students maybe. I just drop one of the observations. So halving is not a big problem. Okay. So then you half it, you do the 2/2, you average, you subtract from the full sample, you then pool, then you do the sample covariance matrix of the subsamples, and then you average across R. You end up with just one matrix. Then you calculate these eigenvalues and eigenvectors. That's it. Then so how you use those? So then we know the eigenvectors and eigenvalues of this matrix now. Now is about consistency and for both estimation of R naught and eigenvectors. Now we already discussed you cannot identify the cointegrating space. Sorry, the vectors you only have up to a rotation matrix H, but you choose any H. So long as non-singular, you can do it. It's not a problem. It's again well known. It's the same in a factor literature. So the key assumption is the rate at which t and n changes. So the way I write this, as I said earlier, is t is a rate of n to power d. Obviously, d has to be positive, otherwise it won't work. T cannot be fixed. But d, we will prove in the thread that you don't need more than, d has to be just above half for this to work, which basically means t doesn't have to rise that fast, as I already indicated. So then, these are very easy to impose restriction, and this is a very simple way of doing it. So suppose somebody is interested in PPP or uncover interest parity of all this kind of thing, then they have a restriction on the B matrix. This is the B dot is a structural parameter, if you like. So this is the restriction on the B, which gives you the structural parameter. Then it's very easy. If I estimate B naught as eigenvectors, so B naught hat is eigenvectors for the first R naught eigen values, which are, say, we assume to be 0. obviously we need to know how to estimate R naught for a minute. Then you can easily get the structural estimate by using this simple formula. It's not a problem. Then you can do inference on the structural coefficients. And these are not easy, by the way. It took me some time to figure out what to do, but with my co-authors. But the details are in the appendix of the paper. So because you need to use basically you need to do everything in VEC form, and it becomes more difficult to look at it. But the key is that this covariance and because of the rank deficiency, right? You can't just look at the whole B matrix, right? So it's only you can look at the part which is restricted. So that's why you need to do these things. But so basically, although we say it's omega Q is basically a sub part of this limit of this QWW bar, right? Everything depends on this QWW bar. As I said, it's required D to be larger than half. And N rise could be very, very large. And then you can then derive the, you want under certain restrictions, suppose this is what the people did. Suppose the restriction you'd put is that there's a triangular restriction. This is actually Peter Phillips lacked. Johansson used the norm so to get the denominator of something equal to 1. It just was convenience he was doing. Then people used triangular. I said, well, triangular is not always valid. That's why I wrote the one I wrote before. So I lack this one. 9 is more general. But if you want the triangular, but people lack triangular form, then things become simpler. You can then immediately look at the vector parameter that you are interested in. You get the usual sandwich formula, you get this, and that gives you the trade-off, because if you want to choose Q optimally, you need to somehow minimize this matrix omega, which we are not doing because we found that actually Q2 works really well, so it's no point becoming more complicated. Okay, so that's the theory. How do I estimate R naught? I thought that initially we thought that we have to assume R naught is known, but then I suddenly realized that actually for this problem is not the same as the problem people have when they try to find out the rank of a factor model or the rank and the way Johansson was dealing with it, because there your distribution is not normal and it's very difficult to pin it down. Here, I realized that quite strongly the eigenvalues which are related to eigenvectors which are cointegrating will be exactly 0 in the limit. Okay, so the question was at what rate they go to 0. I found that goes very fast. So therefore I said, well, it's possible. Now, so what we did then, we said, okay, this is everybody does. So basically you start from the lowest eigenvalue, right? And then you ask yourself, is it small enough? What do you mean by small enough? Is it below a threshold? Was a threshold CT? How you define the threshold is to do with T. You could be with N, because N and T are different. It doesn't matter whether you call it with N or a T. It's just to do with what delta you use, right? So that a small means that for a given delta, there is obviously C. We have to decide what C is, what delta is, but let's ignore that at the moment. Let's just say we know what delta and C is, or we choose it. So you look at the first eigenvalue, you estimate it. If it was below that, you say, oh, okay, there is one vector, R naught is 1. But then you say, but it may be more than 1. So you go to the second eigenvalue. If the second eigenvalue is also below this threshold, we say there are 2. So you carry on till you get an eigenvalue which is not below this threshold. And you say, bingo, we moved into the upper part, therefore R naught is that threshold, that point. Then I thought about it, how do I prove this thing? I don't like this, it's a sequential, right? If you look at Johansson one, you have a sequential. I never liked this sequence because I didn't know really, is it mathematically rigorous enough? Then I suddenly came to this idea with my co-authors that look at 14. you can actually rewrite this, what I just told you, in terms of our hat, like an estimator, which is an average of the indicators. It's the same idea, but you can write it like this. It's another way of writing the idea of what I just told you. Why I like average? Because all statistics about average. So it's an average over M, right? So this is an indicator. So this is 0 or 1. So if it's below the threshold, is effectively it is we say is 0, right? So it's 1, because that if it's below is 1. So as soon as go above becomes 0. So therefore it's exactly what I've just told you in verbally. This is a mathematical expression of what verbally I explained. But the good thing about it is I can calculate how this R hat differ from R naught. So I can find out the rate at which R hat goes to R naught. Okay, so that's the beauty of it, is that, as you know, expectation of this difference is probabilities. So I need to work out the probability that the eigenvectors are above a threshold or below a threshold. And then if you calculate this, because of the eigenvalues are sequential, one is larger than another and so on. So the probabilities become bounded by the first one. So basically everything become R naught. Because if the smallest one is larger, right, then that's one answer. What about if the one at the threshold, when you go above it, is it still below CT? So that's what you need to do, right? You don't need to work out all the eigenvalues. You need to look at the first one. I think maybe the order I didn't see here. I think the order of the eigenvalues, you go from the smallest to the largest, I think. Oh, yes, sorry, I should have said that. It goes from smallest to the largest. I should have said that. Okay. So because of that, you need to worry about the smallest. Do I worry about the largest? No, I worry about the one which is above it, because I want to look at that. If that is smaller than CT, the largest would be smaller than CT. So that the probabilities are bounded. Okay. So therefore, I only need to worry about these two probabilities. Then we just go and do the algebra. That is so fast. I was just amazed. Nobody believed it to begin with. It's because of the pooling. The lowest one go to 0 very fast already. So obviously the CT, I haven't discussed what CT is, but what you need to do, you need to make sure that this probability goes to 0. And then we come back to both this one and this one has to go to 0. Because remember, we want this to go to 0. You want both of them to go to 0. M is fixed, R naught is fixed. So long as these two probabilities go to 0, and the rate at which they go to 0 determine the rate at which R hat converges to R naught. And I don't think there is much time. Then we can talk about why that works. So basically, when you look at these probabilities, effectively, you can approximate it, because n going to infinity, t going to infinity, by some normal distribution because of the pooling. Okay. But if I didn't pool, obviously the distribution wouldn't be a standard, right? You get fat tail, the same as Johansson had when you deal with single country. Okay. And then you can even prove a stronger result, that this goes to 0 at in square terms rather than just in norm 1. It goes with 0 at the norm square as well. So if you then look at t equal to n to power d, then I put that. The only restriction you need to put on delta is delta cannot be too large. So basically you want to let delta to be near 0, which makes life easy, which basically is exactly what it's saying. You want it near 0, so CT is a small to compare with something which is supposed to be 0, right? So that's what the theory tells you need to do. Now, I haven't said you what about C and what exactly delta should be. Now, one of the things one has learned when you do statistical analysis, you want to work with things which are scale invariant, okay? There is no way you can find out optimal way of doing it, in my opinion. So the way we did it is say, okay, I have this QWW bar, which is not a scale free, but I can convert it into correlation matrix. But I'm not I'm not using correlation to average, you know what I mean? I'm not doing that. I'm using the covariance because my theory is on covariance. It's just for the purpose of C, I am using a scale R. And therefore, when I look at the eigenvalues, I don't look at the eigenvalues of Q, I look at the eigenvalues of R. Then I say, okay, I set C equal to 1 now. Okay, it's just that the way I did it. So notice here, now we're switching to eigenvalues of R. But remember, eigenvalues of R, if it is 0, is the same as 0 eigenvalues Q, because these are diagonal. All these diagonal elements are non-zero. Right? It's a variance, it's all non-zero. So then we look at what the delta is. So what we did, we say we should be near enough. We don't want too large, so we tried a fourth and a half. It turns out 1/4 works almost everywhere. Again, I'm sure somebody would write to me and said, could you find the optimal value of delta? Can you try another C value? My approach in life is when I know something works and it's robust, I say, let other people criticize it. And then when people use it, they decide whether it works for them or not. My guess is it would work. Now, if you see some of the Monte Carlo result is extensive. Alex Chudik loves doing Monte Carlo. So I always say yes, more than what we need. Basically, there is a lot of evidence that it works. Basically, we do Varma, it works. You know, if those of you worry about moving average, it's irrelevant to this problem. And also, you don't need to assume direction of causality. I think Jörg that done work on it, that basically most of the co-integration, including the work we have done, I received another new paper from some other co-authors, some other authors just yesterday about it. They always assume the W is split into Y and X. X causes Y. We are not making any assumption, right? Is the W is a vector. We don't say which element causes which other element, a long run causing which other element. And we know that if T has to be large, but doesn't have to be larger than 50 for N to be 1,000. So it works with T, the sample sizes people have with N very large. But anyway, we look at some of the results. But what are the cons of this method? Well, we assume homogeneous long run, right? I just told you. You have to assume the same long run across all units. R naught is the same, and beta naught is the same across all. The second thing is that obviously, if T is very large relative to N, why would you want to use this method? I'm sure, you know, some of other methods developed by many people in the literature could be better. It's like a time series problem, not a panel problem, in my view. If T is very, very large and N is very small, I call it the time series problem myself. No, if N very small, N1, everybody agrees time series problem. Suppose T is a 200 and N is 2. Would you call it panel? Time series. I would call it time series. When would I call N a panel? When I think N become like 30 or 40 or 50, then I call it a panel, in my view. So the way I approach the problem. Now, so the difference really is the D. Now, we're claiming that our method works if D is less than a half, but we are not claiming our method would dominate all other methods if D is larger than 1. Okay. So we are not suggesting that what people have done is wrong, because I'm emphasizing it, because every time I do, people think I'm criticizing other people. I'm not. I'm just saying if D is larger than 1, in other words, T way larger than N, there are other methods you should try as well. I think it still won't work very well, those methods, but that's a different problem. It would be more efficient. So the advantage of this method is simplicity. You can estimate R naught amazingly accurately, to everybody's amazement, anybody who's looked at it so far. And the third is that it works when N is way larger than T. But you assume a commonality of the long run. Okay? But as I said, if you want to assume different long run, I don't know what it means to pooling. So the only way would be to look at the average. So the only way you say, yeah, the long run is really the same, but it's slightly different across these units, right? So that has to be kind of heterogeneity, which I've done a lot of work on. But here, that heterogeneity, by very nature of dynamic, become correlated. So therefore, I cannot allow heterogeneity for this problem in this model unless I do each country separately. Of a new paper I presented in London, which would show that. There's another paper with Lily Yang, which we're just revising, which we show that if heterogeneity is correlated, dynamic model create that, you cannot deal with it in pooling. You have to deal with it by individually, separately doing them and averaging. But that's a different problem. Okay. Now,
Sorry
the
to interrupt, Hashem.
Montgomery
10 minutes.
yeah. So basically, let me just show you some of the Monte Carlo very quickly. So here we do T 20, 50, 100, but we go N up to 3,000. And then and also use the pool, the R squared to be small, because I don't think this panel have, so people run Monte Carlo with the R squared, they don't even report it. It's 0.8. I mean, it never happens in real world. So you need to choose that small, by the way, guys, if you want to do it. If you look at it, the first time Alex was writing, he said, we better not put this table, which is all 0 and 1. I said, well, at least people see it. There is a one which is not 0, 0.05 is the error. So if you don't believe it, do it yourself. In fact, this model has a F in it. There's a factor in it. But it's I naught. But then we have a result which is, so therefore you can estimate R naught really well. And then what about if you do the cointegration, given the R naught, you have got that, you use Q2 subsample. These are the root mean square error, goes down very, very quickly. And then the size is controlled. Obviously, you can't control the size if T is fixed and then go to infinity, right? We don't say that because remember, T and N has to go together. But it's about the same rate because of the root square. It's just about right. And then we have checked Garch, I1 factors, all sorts of things that we have done in order to robust. Because my view is that there's no point. I think what I'm developing with my co-authors is a product that the researchers can use. It has to be robust. So we have checked a lot of robust issues in it. And the application is a twofold. I don't have the time to go to application really. But basically, one of the application deals with compute stat data. So that's one purpose is both financial data. People use all these ratios in financial analysis, but nobody knows they are co-integrating or not. But that's a different story. So I'm going to stop here and look forward to hearing your comments as well as, most importantly, the discussant, which his work I know well, and I respect his comments way above many other commentators. Thank you very much.
Thank you very much, Hashem. That was a wonderful presentation. So I'll turn off the recording now.